Alexandra is a market team leader at Technoform North America. 10 years of experience there at Technoform, drives innovation, technical collaborations, and industry academic industry and academic partners, actively contributing to industry associations such as the Facade Tectonics Institute and the Fenestration and Glazing Industry Alliance. So she's here to talk about condensation. Alexandra, please.
Thank you. Happy to be here. So I apologize, Helen couldn't join us today, so I have some big shoes to fill for this presentation. But basically, we're working with a university in Massachusetts in North America to really dive into the details of condensation. We're basically, focusing on the edge of fenestration and how we can thermally improve fenestration, but also this really has a high impact on what's then happening to condensation resistance. So first, I'll just kind of give a brief overview. I think many of you probably know kind of this connection between glazing and condensation performance, but how it's really related to the edge of glass and the framing. And then I'll just kind of go into really the details of this study that we did with the University of Massachusetts, and then finally end with some conclusions for fenestration. So before we even really talk about condensation, we have to really talk about thermal performance and how heat transfer is flowing. I think there was also another presentation yesterday that was showing some percentages about conduction versus convection versus radiation and where the thermal bridges are really happening. For us, this is kind of our view in the North America market. So much of the thermal bridging is coming through conduction. So it's really about the materials and their thermal conductivity values that are really driving then what's happening on the edge of glass, which is then driving condensation resistance. Okay, so we have 3 different rating systems, basically, in North America. We focused on condensation resistance value. There's a newer index, this condensation index, that's been coming, that's supposed to be a little bit more precise in terms of how the method is kind of correlating to the actual condensation extent. But one of the challenges is that, of course, these are all measured and calculated under specific conditions. But what we were really interested in understanding is how does this actually then translate into how much condensation you might see on the perimeter of the glazing or fenestration. So focusing on condensation resistance, it's basically on a value scale of 1 to 100, 100 being basically a perfect system that's never having any condensation. And typically they're using these relative humidity values of 30, 50, and 70. We looked at 30, 50, and 60% for the conditions. And just to kind of explain the importance of why really the perimeter is mattering so much when we talk about these calculated values. So for example, we can start with a relatively high center of glass factor, and then starting with really not a lot of thermal breaking, so high thermal bridging with an aluminum spacer and a non-thermally broken frame. And then we can improve the center of glass. And it's really not making a huge influence on the condensation resistance value. But then if we take that same kind of higher center of glass value, lower performing glazing, and then we start to incorporate a warm edge spacer, and then also a simply thermally broken frame, it's having a really big influence on this condensation resistance value as it's calculated. And then we can add on top of that to move to a best-in-class thermal break, and then we're basically able to improve this even further. Obviously, we're at Technoform focusing on plastic hybrid stainless steel, so a little bit different technology than what Chris was presenting. But essentially, what we're talking about, what I'll show you in this study, is really focusing on the thermal conductivity. So it's really not making so much a difference of the different types, but really the conductivity of the spacer is actually making a big influence, and also in the thermal break. So we wanted to really kind of understand how does this actually correlate to what we could expect on an actual glazing unit. So we were looking really more at a simulated situation, but using THERM, LBL, as Stephen Selkowitz, I think, is maybe somewhere in the audience. But we were basically using THERM to simulate for a variety of aluminum framing systems, and then also a variety of thermal performance in the glazing. And then we were really a quite simple procedure, so checking the temperatures along the interior edges and surfaces, and then determining, okay, is the surface temperature at or below the interior dew point? If yes, then we're seeing condensation there, and then what we were doing is measuring that total extent, and then comparing this across a range of system details. Okay, so these were the variables that we were basically experimenting with. So for center of glass, ranging from double plane with one low E coating, or even none in some cases, air or argon filled. Triple panes, we basically skipped the air and went straight to argon fill with 2 low E coatings for really high performance glazing. And then for the frame, we were doing a range basically from having no thermal break and then all the way up to having these really complex shapes with foam filling. And then for the edge of glass, basically toggling between an aluminum spacer and a worm edge spacer. So these were basically a representative sample of the system details that we were looking at. And what we tried to do is to basically find system details that would give us a wide range of U factor, and then also a wide range of CR value. So we started with a really poor performing system with basically even a air gap in it, and then non-thermally broken, then going all the way up, as I said before, with these more complicated thermal breaks and foam filling and glazing. So just to kind of summarize our findings before we get into the details, we kind of already knew this as an industry, that U factor and CR are not really perfectly correlated. There's definitely some sort of general improvement of condensation resistance as you're improving thermal performance, but they don't exactly correlate when you talk about condensation extent. And then when we look at really the window system details, we basically determine it really goes back again to just some basic material science. So what is the thermal conductivity of the different components, and any of the weakest links are really driving that condensation resistance, kind of like energy or water, so always going the path of least resistance. Having a thermal break, of course, and a worm edge spacer reduces this risk, kind of going along the same thought process, improving thermal performance. And really this was also confirming, in the same way that we think about thermal performance, is that it's best to really start at the frame first, and then you can start having a larger impact when you're adding a higher performing spacer and center glass. So what I'm going to show you now is basically the system details at the worst condition that we were modeling at basically roughly negative 30 degrees C. We were ranging from about 0 degrees Celsius down to negative 30. And then interior relative humidities from 30, 50, 60, but here we'll show basically the worst condition for comparison. So starting with basically a non-thermally broken system with a really pretty poor CR value, U factor. You can see that in both of these systems, even when we're making a almost twofold improvement to CR, this is really not having a huge effect when you're adding the worm edge spacer, because the frame is so poor performing in the first place. So it helps a little bit, but not too much because of the frame performance dominating. Then when we add this 1-inch thermal barrier, and we're comparing an aluminum spacer to a warm edge, basically then the edge of glass is now driving that performance further. Here we don't even have really, actually we have a worse performing glazing package than we had here with the low E surface. Yeah, so basically this really just kind of, again, confirms what we knew anyways about thermal performance, is that first starting with the frame and then kind of tackling the edge of glass. Okay, so, I think something was happening with my slides, but basically if we look at this system here, which is it's like a 1-inch thermal break with an aluminum spacer, and then we're comparing this to one, changing the spacer type, and then two, leaving the spacer type the same, aluminum spacer, and then changing the thermal break to a wider, it was 44 millimeter thermal barrier, and then also improving the glazing package. Generally, what you see is in the calculated values for condensation resistance and U factor, of course, we're kind of going up in this linear path. But then what happens when we actually look at the condensation extent? Going back to the first system, of course, this one's the worst performing, but then you start to really see that the spacer conductivity is really driving the condensation resistance. So what was interesting to us about this is that actually when you're, then improving the thermal break and then adding a better glazing package, even with an aluminum spacer, you still are getting a higher condensation extent, even when also the CR is rated higher as well. So it's basically just pointing out the fact that a rating system is just that, but it's not really telling us like the details of what you could expect in real life. So then when you start adding a warm edge spacer, once you've really like improved the thermal barriers and the framing, then the extent of condensation is really reducing tenfold. We also even see that in the previous systems. You can kind of see these linear extents that we're able to kind of improve this by multiple factors. And then when we started looking at these higher performing systems where we're adding like foam fill and more complex shapes, and we see kind of the same trend here. So we started adding also a better glazing package with low E, argon filled, and we're seeing kind of this same sort of tenfold improvement in condensation resistance. Finally, same story again with the triple glazing when we're really significantly improving the glass package. What was interesting about this is that this wasn't having any condensation, but then what we also did, because we were curious, okay, then what's happening when you try to take this to failure? And so we were taking this down to something like negative 75, like C or something really, really like extreme conditions. And even then, there was no condensation. So it also brings up some questions about maybe the limits of the modeling and the simulation software as well. But yeah, we found this pretty interesting. And what was even more interesting is this is rated at 67. Again, CR is on a scale up to 100, so you would think that a system like this that is having no condensation at these really extreme temperatures would actually be much closer rated to like somewhere around 90 or 100. So there's some gaps here when you look at the details of CR. So really to summarize the takeaways from this study that we did, the condensation resistance is really driven by the individual components, and again goes really back to just some basics about the material properties and conductivity. So it means the frame, the spacer, the center of glass. And what we're finding is that these windows with similar U factors and CR values actually in reality are performing a bit differently in terms of the amount of condensation you could expect along the different components on the interior side. And really, this is following these same properties of electricity or water that, thermal bridging is happening, going the path of least resistance, and then that's having an effect on the condensation that we could expect. So to manage this, it's, again, kind of, for us, was confirming what we already sort of knew about thermal performance is, one, you should always start with improving the frame with wider thermal barriers, but there's a kind of like a cap to that as well. So at a certain point, you can start playing with the glazing package and having a higher influence once you get to a certain thermal barrier in terms of width. And then next step is really improving the edge of glass and then also the center of glass, because once the frame is improved, you can have a higher influence there. And finally, really to specify, I mean, glass is typically already pretty specific in terms of center of glass performance, but for the frame, really, being specific about the size of thermal barrier, the performance that you want to see out of the framing system, and then also really getting specific about the worm edge type and also the edge of glass effective conductivity. Again, as I said before, we're, of course, we're selling some specific products, but this goes really back, again, to these basic principles of thermal conductivity and really making sure that you achieve this balance between the components and that you don't have one component that's really high thermal conductivity with a component that has a very low conductivity, because at the end of the day, your lower conductivity materials then not really you're not getting as much out of it as what you really could. And with that, I'll leave it a little bit early and open it up for questions.